Today in this lecture we are going to prove the argument principle. So the statement of argument principle is, let C be a simple closed contour described in the positive sense and let F be function object be a function which is analytic inside and on C, except passively for poles interior to C. Also let FZ have no zeros on C. Then 1 by 2 pi delta C argument of FZ, this is equal to n minus p, where n number of zeros inside the closed contour C and P is equal to number of poles inside the closed contour C, and counting multipliers and both are counting multiplicities. Proof By argument theorem we have the figure in z plane, or we say n minus p, this is 1 by 2 pi I integral over c f dash z upon fz dz. Now the figure in z plane is like this. Suppose this is z plane, z naught is suppose this point, this is the contours c, and the figure in w plane is like this. This is suppose gamma. Let this point be w naught and this point be w starting from these points. Since fz has no zeros on c, the contour gamma does not pass through the origin in the w plane. So this is w planes, this is uv axis, this is xy axis. Let w not be any fixed point on gamma, and by argument principles, as we know, n minus p, this is equal to 1 by 2 pi I integral c f dash z upon fz dz. So this gives 1 by 2 pi I the integral of these functions will be log of fz over the contour c, and this will be 1 by 2 pi I, and this is delta c log of fz, and this is 1 by 2 pi I delta c log of mod of fz plus I, here 2n pi plus theta. For the principal argument n is equal to 0, principal value n equal to 0, we have 1 by 2 pi I, here delta c log of mod of fz plus 1 by 2 pi I, and here I delta c argument of theta. So here theta means argument of fz, where delta c denotes the variation of log of fz round the contour C. So this gives 1 by 2 pi I delta C log of mod of fz plus here I will be cancels, so we get 1 upon 2 pi delta C argument of fz. Since delta C log of fz equal to 0, if we suppose if we take a circle like this, and if you start from these points and move around this, and we again reach at these points, then delta C log of fz mod of fz will be 0. So 1 by 2 pi I into 0 plus 1 by 2 pi delta C argument of fz. So this gives 1 by 2 pi delta C argument of fz. Hence 1 by 2 pi delta C argument of fz, this is equal to n minus p, where n be the number of zeros inside the contour C and p be the poles, number of poles inside C, and counting multiplicities. Hence the theorem is proved. For example, if fz equal to z square plus 1 whole square divided by z square plus 3z plus 2 whole square whole cube, find integral over C f dash z upon fz dz, where C is the circle, mod of z equal to 3. Solution: since fz equal to z square plus 1 whole square upon z square plus 3z plus 2 whole cubes. So zeros of fz are given by z square plus 1 whole square equal to 0. This implies that z plus I, z minus I का whole square is equal to 0. This implies that z plus I का whole square, z minus I whole square, this is equal to 0. This implies that z equal to I and z equal to minus I are repeated poles. So total repeated zeros, not poles. So total number of zeros this is equal to 2 into 2, that is 4. Now poles of FZ are given by, again, z square plus 3z plus 2 whole cube is equal to 0. This implies that so z plus 1, here z plus 2 whole cubes, this equal to 0. So this gives z equal to minus 1 is a pole of order 3 and z equal to minus 2 is a pole of order 3. So the total number of poles, this is equal to 3 into 2, that is 6 by the theorem we have 1 by 2 pi I integral over c f dash z upon fz dz. This is equal to n minus p. This implies that integral over c f dash z upon fz dz, this must be 2 pi I into n minus p. So this gives 2 pi I, and here we see that all the zeros and all the poles lies within the contour C, because the figure is mod of z equal to 3 is like this. Suppose this is x-axis, this is y-axis. So the coordinate of this point will be 3 0. This coordinates will be 0 3. This is minus 3 0. And this coins will be 0 minus 3. Coordinate of this. Here the z equal to I, 0 z equal to I is suppose here, minus I is here, and z equal to minus 1 is suppose here, and z equal to minus 2 is suppose here. So all the pose lies within the contour C. This is contour C. mod of z equal to 3. So the total number of zeros here will be 4. A total number of poles will be here 6. So this gives 2 pi I into 4 minus 6 minus 2. This is equal to minus 4 pi I. Therefore, yeah, or we write hence integral over c f dash z upon fz dz, this is equal to minus 4 pi I, which is the required solutions.